Hello, my name is Tim Holey. I am starting a short course on advanced scientific computing. This is the first lecture in that, and this course is going to be offered in the Julia programming language. And so this first lecture is really essentially just telling people why Julia is an interesting language for scientific computing. So Julia was created with a couple of motivations, and the most important one was really to combine the ease of programming in high-level languages, similar to Python, R, and MATLAB, with the performance of a low-level programming language like C or C++ or Fortran. And historically, there has been a very large gap between these different sort of layers and styles of programming, but it doesn't actually have to be that way. And so the problem that comes about when you have this split between easy to use languages and high performance languages has been called the two language problem. And that is that a standard sort of workflow that gets sort of forced on you is that you do your exploratory thinking and planning and analysis and design in the high level language, which is very efficient to try out many different things and see how you like how they worked out. And you go on that way as long as you possibly can. But if you get to a point where you have a step in your analysis pipeline or computational pipeline where the performance is really essentially unworkable, then you have to sit down and rewrite the very performance sensitive parts in a language that's more efficient than whatever you started out with. And then you try to make it so that you can call the more efficient code from your high level language, basically. And that's great, and it's been done many times before. There are many good examples of that. So if all of your work is at the level of, say, matrix multiplication or sorting or something like that, the odds are that your programming language is doing just fine performance-wise. And the reason why is because a lot of those tasks have already been implemented in a fast language, and you can just call them from your programming language of choice. And if that really sort of describes everything that you do in the world, then you have little to gain by from a performance standpoint anyway, of changing to another language. However, that actually, for people who do rely on computing, that turns out to actually be quite rare. And so the problem is that most people do eventually run up against something that they need, but which has never been written in a fast language. And if that happens and you're pushing the research frontier some way, that you're up against a problem no one else has had to solve before, now it's up to you. You are the one who has to resolve this issue. And if you're not equally comfortable in both a high level and a low level language, or don't want to spend the time that it would take to write it in a low level language, it can be a very frustrating experience. And so people, again, do everything they can to circumvent this problem. One of the bits of advice that's very common in some of the slower high-level programming languages are to vectorize everything, which basically means pass large chunks of data to C, C++, Fortran routines, so that they can take over and do a lot of work rather than a little bit of work for essentially one passage of data to them. Sometimes that works, but a problem with that approach, even when it solves your performance problem, is that it sometimes kind of makes your code pretty ugly. And I'm just showing an example here that was pulled off of MATLAB Central, a forum for people who used MATLAB. And what you can see here is the solution, and it's reasonably short and elegant, but it may not, to an interesting problem, and that is that if you have an image and you want to blur it just a little bit, you're just going to blur each pixel against its just a ring of neighbors right around it. But you have to do something special at the edges, because at the, say, top edge of the image, there are no pixels above it. So those neighbors are missing. And if you don't want to just fill everything in with zeros, you don't want to sort of make up data, you might just say, well, let me just simply blur against the, say, 6 neighbors, including myself, that I have if I'm sitting up against the top edge, right? So take the average of the 3 pixels in that row that are closest to you, and then the 3 pixels that are in the row below that. You have to do special things then at the left edge, the right edge, and all of the corners of the image, and this ends up, resulting in a a bit of code that really isn't all that, I think, easily readable. And so, this is a very common experience when you're forced to vectorize everything in order to get decent performance. And so one of the things that has really sort of, I think, changed the landscape in this area a lot was the creation of a relatively new programming language called Julia. And it was actually started in about 2009, but its development was relatively quiet, but it really burst onto the public scene with a now famous blog post called Why We Created Julia. And if you're interested, I strongly recommend looking up the original, but it sort of shares their overall goals in having started this effort. And the fundamental effort was to end this two-language problem by creating a high-efficiency, easy-to-use language, high efficiency from the programmer's perspective, that also had excellent computational performance. That has turned out to be a very attractive goal to many people, including myself. So just to give a little bit of history here, my lab was one of the developers of a technique called light sheet microscopy. We were the first to use it for calcium imaging. Right around the time they were working on Julia, my lab was struggling a lot with big data, and discovered that I was spending so much time rewriting things in C that I was spending more time rewriting and writing glue code to be able to call the C than I was writing real code. And so I began to question whether my high-level language was really saving me any time. And so I started thinking about rewriting everything in C, but I was loath to give up the sort of interactive development experience you get with a high-level language. And I happened to just do the search at just the right time, where I stumbled across the famous Julia blog post. I didn't see it when it came out. And after some initial interaction online and getting really excited about the utility of this amazing language, I actually started to join the developer team with my first Julia commit. And this has become, for me personally, a big thing. I've done a lot of work in many different areas in Julia that span from array handling to the compiler and a lot of developer tools, among many other areas. I would say that for me, that part of the reason that I do this is because it's a way to make a real impact on the world. So at this point, the community of people who have developed Julia, and it's a very, very large number of contributors by this point, more than 1,000 contributors, have really started having a lot of impact. So this is, even somewhat dated, but the numbers and growth rate in the community is very, very large. It's, somewhere around every 14 to 18 months, most measures of Julia's adoption double, basically. And a lot of this is based on real major milestones. So in 2017, Julia became the first language besides these sort of most widely used high performance, low level languages to break the so-called 1 petaflop barrier. You don't do that on your own laptop, but on a large, national lab scale computer, it is possible to do so. And Julia was the only language besides those to do that. In 2018, we released Julia 1.0. And we entered, some of these lists of top programming languages for the first time. We've been rising on those lists very, very considerably. One of the most impressive measures, I think, is that the number of attendees of our conference has been growing like crazy. So in 2019, we were in person, and we had somewhere in the ballpark of about 500. And we jumped to 10,000, a little over 10,000 last year, and a little over 20,000 this year. So this is an enormous, explosive rate of growth in conference attendees. Courses taught in Julia are becoming very influential. We have a lot of people working on the language. There are 3 to 8 new packages released on average every day, and lots of new versions of established packages get released every day. So overall, the ecosystem is really growing at a phenomenal rate now. And you might ask why. So this is part of what makes it, I think, viable for programmers of all stripes to start considering adopting this language. It's not just for a few people with extraordinary demands at this point. It's starting to reach down into more and more daily usage by larger and larger pools of people. So what are the things, what are the features of Julia that have attracted this attention? And what are some of its remaining negatives? Because it unquestionably has some of them. That's something I think about a lot as someone who works in the language, is mostly sometimes about the negatives, but it's very important to celebrate the amazing things that it does too. And so I would just simply describe these as sort of three key features that it has. One is it's a new and modern language that has a bad side, which is as fast as the package ecosystem is growing and as good as it is, and as solid as the trunk of it is, once you start getting out into the little twigs, you will sometimes find things that no one has ever used Julia to do before. And you may have to decide whether you want to write that yourself or go use a language that someone else has done something analogous before. There's obviously a huge plus to having a new modern language. In addition to the performance, which I'll demonstrate in a little bit, it's also just very, very elegant and has many user advantages for that reason. Perhaps the most wide or impactful feature of Julia is that it does something called aggressive type specialization and compilation. This is really crucial to Julia's high performance. And this again, it has a downside, which is that compilation takes time. And this therefore adds to the latency the first time you do something in a session. I'll mention a specific example of that in a little bit. But on the flip side, this is the source of its amazing runtime performance. So if you're willing to pay the latency because your runtime computation is much longer than the latency, this is an enormous win for your needs. And then the final really key feature of Julia is it's really fun to program in. It's a very, I think, beautifully designed language. The packages in its ecosystem are composable in ways that aren't always true. In fact, are sometimes, I guess, rarely true across some of the rest of the ecosystem. And it makes the code that you write very, very reusable and generalizable. So I'll spend most of this lecture talking about these specific features and illustrating some of the pros and cons. And I think they are mostly pros. So I've found that it's, one way to just sort of emphasize some of the benefits of a modern language, or just sort of the freshening of the look that you can get from the language, because that doesn't require any deep understanding of syntax or anything like that. And so one of the things that happens when you start a new language in the Unicode era is that you can make that essentially a native thing in the language itself. So if you were to, in Julia, write a function that would compute the Cartesian coordinate representation starting from spherical coordinates, you might write it this way. And what you'll notice is that we're using Greek symbols that have very well established mathematical meanings to them. And I think anyone who knows the underlying mathematics and looks at this is well equipped to understand what this means. This goes even further than this, in that it's even possible to use emoji in your code if you want. And this is a Julia representation of the famous predator-prey equations, where you can see that the number of mice is increasing in proportion to the mice as they breed, but decreasing as they get consumed by cats. And likewise, the number of cats grows as they eat more mice and diminishes as they die of old age or other factors. So the usage of symbols does not stop directly at Greek letters. This is a pretty uncommon kind of thing, but the usage of standard mathematical notation is widespread in the Julia community. And I think it really enhances the readability of a lot of code, right? This is first line, any mathematician would probably guess that this is asking whether 2 is an element of a set that includes 4, 5, 6. You might not know that it includes 7, but it also does. And so it is not, for example. And this is asking if this subset, or if this is a subset of the list of integers from 1 to 5. These represent a function, its gradient, and its Hessian. And again, no one really needs to know much Julia syntax if they know underlying mathematical representation to be able to understand what a function that is given this as its function name actually conveys. And so it, for code that is read more often than it is written, it's often very nice to be able to choose symbols that mirror, for instance, the paper that you're following or something else like that. Another place where the fresh design of Julia, I think, is a huge win is in plotting. Julia has a wonderful plotting package called Maki, and it is capable of producing just some amazing interactive plots very elegantly and easily. This just shows a couple of GIFs that I took off of the Maki website. And you can see here a slider that the user is dragging interactively back and forth, and you can see how the entire rest of the plot is updating in response to sort of show the actual underlying data in greater detail at the particular time periods that that slider is selecting. You can run sort of elegant real-time simulations and interact with them in meaningful ways where you change some of the parameters of them. And I think, examples like this really illustrate in part also that, Maki starts blurring the lines between sort of a general computer graphics infrastructure and that of plotting. And that, I think, is a very long overdue blurring in many ways. And it really adds, I think, a lot of new capabilities. And there's a whole Twitter page, which I urge you to check out sometime, where people are uploading daily amazing new pictures of the graphics that they're using Maki to produce. So it's really, I think, a plotting framework that's worth envying and emulating in whatever other developments of programming language plotting suites there may be. Maki only has one really big weakness in my mind, and it's a big one, and that is this latency problem that I mentioned. So for all of its elegance and beautiful design, the first time that you load Maki in a fresh Julia session and send your first plot to have it pop up on the screen, you could easily end up waiting 35 seconds for that to appear. And that's just all the time that Julia is spending aggressively specializing and compiling Maki's code, basically. So, when you send your second plot, it may pop up essentially instantly, right? And everyone, for as long as you keep your Julia session running, that it should be fairly fast. Even there may be some lag, but even if you start changing up your plotting, still you've compiled a lot of Maki, presumably, and so it's fairly efficient right after that first plot. But the first one's a doozy, and that's a big negative of Julia. If you are interested in Julia and in using Maki, because it really is a gorgeous, gorgeous plotting framework, there are a couple of things you can do. One is keep your session running longer. And for that, a package that I actually wrote called Revise, which lets you do live updates to your code and your running session, can be quite handy. The second quite popular strategy is to use something called Package Compiler. And this allows you to basically build a system image with your favorite packages pre-compiled. So basically what you do is it effectively launches Julia. It loads the packages you've decided to include. It gets them doing all of this work and paying this latency cost, but then it takes a snapshot of your system and saves it to disk. And this essentially means that then if you just start Julia from that snapshot instead, that cost has essentially already been paid. And so it's much faster. There are downsides to using Package Compiler. It basically freezes you into a specific set of package versions. And so if you're a developer like myself, I almost never use it simply because it gets in my way more often than it helps. In the long run, and hopefully the long run isn't too far away from now, we're, I think, all hopeful that we'll have this resolved much more elegantly. But this is, I think, a genuine negative you need to be aware of if you're contemplating using Julia. So what do you get, though, of course, for all that latency? And what you get is truly extraordinary. So these are a couple of figures of panels from a paper we, in collaboration with quite a few other people, just put up a little bit ago. And what it shows here is a couple of biological tasks. One on doing network inference on a set of single cell networks. And what you can see, for instance, you're comparing R, which is a very well-developed, widely used language for doing this kind of analysis, and how its runtime increases as a function of the number of genes that are in the inferred network, versus Julia doing the same task in the green. And what you can see is that the Julia algorithm is really outperforming by the time you have quite a few genes, more than an order of magnitude R's performance on this particular task. Shown on the right is another comparison between Julia and this time several other different programming languages, and it's a solution of a set of ordinary differential equations in that famous predator-prey equation I showed you earlier. What's shown on the vertical axis is the running time again. So again, higher is worse. Note that this has already been log transformed, and this is by factors of 10. So the gap here between this sort of group of green lines and blue lines is about 100-fold. And what you can see is, while the running time does depend upon how precise you ask it to be, if you're willing to let the algorithm be sloppy, it finishes a little earlier than if you ask the algorithm to be very, very precise. But what you can see is that across the board, these green lines, all of which come from Julia code, beat the blue lines, which amazingly come from both C and Fortran, two nominally fast languages, and by a league, far more the lines from MATLAB, Python, and R. And so these are orders of magnitude differences that are they really can determine whether something's possible or not. We're starting to benchmark some of the image processing code in Julia. This is an area that I've made contributions to. We're really just getting started on this effort right now. But what you can see if you compare Julia, again, now runtime on the vertical axis, higher is worse. This time I'm computing the ratio of running time compared to Julia. So things right at the dashed line, it's effectively a tie. If they're below the dashed line, that means they're doing better than Julia. And if they're above the dashed line, they're doing worse than Julia. What you can see is that in the image processing domain, when you can apply it, the only sort of serious performance competitor for Julia is this C++ framework called OpenCV. And it truly is an amazingly beautiful package. But Python and MATLAB are often an order of magnitude, sometimes 3 orders of magnitude slower than Julia. And there seems to be a trend towards it. These are sort of more basic tasks that don't depend on image content. These are more sophisticated tasks that do depend upon the image content. And while it remains to be seen whether this will hold, it looks like a trend is that the more complicated the task, the greater the advantage to Julia. So again, what's I think again maybe surprising about this is that a lot of the code that's in Python and MATLAB is nominally compiled C code, right? And yet you see that the Julia code is leaving it in the dust. And as I'll sort of get to by other means later on, actually often much more flexible at the same time. So, these advantages are really non-trivial. One last case that I'll give shows you a really interesting wrinkle about performance, and that is that there are almost sort of 2 definitions of fast. And I'll elaborate on this a little bit more later. But this shows this task that I mentioned before, which is sort of matrix multiplication. And this compares the running speed of a number of different implementations as a function of the matrix size. They're all square. And what you can see is that in this case, it's represented differently. In this case, it's the number of floating point operations per second. So higher on this plot is actually better now rather than worse. And you can see that there are some very, very large gaps in performance here. Interestingly, all of the curves here are for high performance languages. None of them are generated for, let's say, just an intrinsic, say, code in Python. If you wrote it out in loops or something like that in Python, that would be really essentially down here along the horizontal axis. So it's not even sort of making it onto the chart, so to speak. There's a set of curves really quite low, and these are what I think we would call naive implementations in fast languages. So in Julia and C, a little bit better than those 2 is Fortran. So a naive implementation of Fortran performs slightly better than those other 2. But you can see they're left, they're as nothing compared to some of the performance of other approaches. And in these other cases, these are much more aggressively and thoughtfully and carefully designed approaches to the same problem that pay an enormous amount of attention to very specific details of how to use the CPU hardware. And so there are some, a few cases where a good compiler can come up with at least some improvements, but in order to really get the best performance, your code has to essentially be handwritten. So one good performer is a famous C++ library called Eigen. Another good performer is this OpenBLAS suite, which has been written in Fortran. Of those, the one that does even a little bit better at these sizes, at least, is the so-called Intel Math Kernel Library, or MKL, and that's probably the most widely used library to implement matrix multiplication across programming languages. Chances are fairly good that if you're using one of the other high-level languages, then it's just calling MKL for its matrix multiplication. But amazingly, the fastest one on this chart is actually written in Julia using a package called Loop Vectorization. And you might think, wow, that must be some really complicated Julia code. And nope, it's not. This is what it looks like, right? So this is just a naive implementation of matrix multiplication. We're just iterating over the rows and columns, and multiplying them and summing them up and stashing them in the output. But it does have one important feature. We've used this package called Loopback Vectorization, and we've put this at turbo in front of the series of nested loops. And loop vectorization is doing all the heavy lifting for you, so it's doing a very impressive amount of analysis. It's actually simulating many different approaches to the implementation of this algorithm. If you know about SIMD pipelines, all this kind of stuff, it's trying out lots of different ways of implementing this and estimating their runtime performance, and then picking the best one and compiling that. And this achieves truly remarkable results. And what's nice about it is that, the hard work of this is done in the design of the loop vectorization package. And for code that fits the sort of stereotype of code for which this is applicable, and not all code does, then just all you have to do is put this at turbo in front of it, and you get the benefits to code that you yourself write with very little effort. So, this is very impressive performance, and it's very usable performance on a wide variety of tasks. It doesn't require a world expert on CPU hardware to design a bit of code for every single algorithm on every different kind of CPU architecture. Okay, so I hope you're impressed by Julia's speed. It really is extraordinarily impressive. And it really is sometimes the difference between being able to do something and not being able to do it, right? And I want to give you at least some hints about where that speed comes from. And actually, here's where I want to introduce this difference between kinds of speed, right? So the example, especially with loop vectorization that I showed you at the end, that's an example where Julia is sort of truly fast by any meaning of the word. But what I want to say is even more ubiquitous, something that can affect every kind of programming and not just programming that's of the sort of stereotype of matrix multiplication. Maybe the even better or more precise thing to say is that Julia's key feature is that it isn't slow. And what do I mean by the distinction between being fast and not being slow? And that is that slow languages, what they do is they get in the way of using the hardware. They introduce extra obstacles. And languages like C, C++, Fortran, and Julia make it not slow by removing those obstacles and simply letting the hardware sort of do its job as intended, if you will. And again, the reason why this is such an important point is this kind of optimization is available to virtually any kind of programming you might do, and so it really is something you can take advantage of in almost any kind of code you write. And so to go into detail about what I mean by a language being not slow, let me do one quick illustration of the importance of so-called types in computers. So you may know that all data in computers is represented as a series of zeros and ones called bits, and they're organized into bytes. And so everything on your computer, every bit of data, has a representation in terms of bits. And so in Julia, I can ask for the bitwise representation of the integer 5 this way, and you can see it spits out this sequence of zeros and ones. Now, what happens if we look at 5.0? So 5.0 is the notation for a so-called floating point number. Mathematically, 5.0 is exactly identical to 5. It's just a distinction that is a computing distinction, not a mathematical distinction. But you can see that this number actually has a different, so even though it's mathematically identical, it has a different bitwise level representation. And you can see there's some similarities, like this sequence of 101. It's no accident, but these are clearly very fundamentally different representations, even if they mean mathematically the same thing. And like you could interpret this sequence of bits as an integer, and you would get an integer that is vastly different from 5. And so the point is that the bits alone are not all you need when a computer has to be able to do something with data. It has to know the sort of the meaning of those bits. And that meaning in computing is conferred by types. And so in particular, it's actually a different set of CPU instructions to add two floating point numbers together than it is to add two integers together. And so the issue then in a slow programming language comes partially, at least, down to the fact that they have a very hard time knowing in advance what type things are. So if you might imagine the way a slow language would implement the addition of two numbers is they're deep in the internals in a place where you don't see it. There might be something that does something along these lines. Basically ask, if they're both 64-bit floating point numbers, you're going to add them together using a particular routine that essentially just calls instructions that execute on the so-called floating point unit on the computer. And if they're 32-bit floating point numbers, you do the same, except you use the 32-bit equivalents of those, because those bits are actually different than the 64-bit ones are. If they actually turn out to be integers, then you're going to call yet a different set of CPU instructions, this time on the core CPU, and 32-bit and so on. And if you test as many cases as you want to provide or are able to provide direct support for, and all of it fails, maybe it's because they aren't even the same type as one another. So in that case, you might convert them both to a common type and then add them, right? And so the point is this, is that each one of these decisions about what to call may only take a nanosecond or so, right? But the process of figuring out what you're working with and then figuring out which routine you're going to use and all that kind of stuff has to be, in some cases anyway, has to happen for every single operation you do on the computer. And that process may be, in some cases, 30 to 100 times slower than if you knew in advance what types you're working with and you could just pick one of them, okay? And that's what I mean by slow languages just get in the way of the hardware. The hardware is really doing work here, but you have to make decisions at each stage about which part of the hardware you're going to assign the work to in order to implement the computation. And that's sort of the barrier that slow languages erect before being able to achieve efficient computing. And so in languages that aren't slow, the types are known in advance, right? And in languages like C and Fortran, those are, you actually declare the types. And so if your code is processing them at all, because you've essentially forced it exactly what types each variable has, for example, right? But in Julia, you don't have to annotate the types of arguments to functions, for example. And in fact, our functions methods can be written generically so that they work on many, many different types and then do the right thing at the sort of lower level calls with each one of those types. And so Julia, in order to solve this problem of wanting to know, in advance what the types are going to be, so it doesn't have to check at every separate instruction what it's supposed to do next, it does a process called type inference, and that basically is prediction and it better well be accurate, of the exact type that each variable will have when you get to that point in the execution of your code. And there are attempts. This is not an entirely new idea, and indeed, both MATLAB and Python have put some effort into improving their performance, and in some cases, they've been able to find ways where they could deduce the set of types for throughout a for loop or something like that. And when that happens, it has a very dramatic benefit for the performance in these otherwise slow languages. But and it should be said that in fact there have been quite a few attempts. I think I know of at least 3 major attempts in Python alone, and the people who were trying to do this are really, really good. And so it's not any lack of effort, it's not any lack of resources, it's not any lack of brilliance on the part of the people doing it. The problem is that this is something that wasn't really, I think, appreciated as being important at the time those languages were designed. And so the languages are not built in a way to make it possible to solve this problem in general. So you can solve it and you can make these predictions in special circumstances, but doing it generically is not reliable. But Julia, in contrast, was designed with an understanding that this mattered. And so it was built from the ground up in such a way that the very structure of the language makes it possible for type inference to succeed the vast majority of the time, not just like in one function or in one loop, but actually in some cases throughout your entire computational pipeline. Many layers of code calling code calling code calling code. And so this really then means that Julia can predict the entire pipeline's types, for example, and this means it never has to waste time asking what something is. Now, Julia is capable of doing that. There are circumstances, even in Julia, where you'll get to a place in the code where it's not either because you haven't written it in the most idiomatic Julian way, or because it's actually something you can't predict. Like if you're loading a variable from a disk file, and that disk file has a type that's sort of self-describing and not predictable in what order different variable types are stored. There's no way in that circumstance to predict what type of that returned variable will have before you get going. And so in those circumstances, Julia does what is effectively the same thing that some of the other slow languages do, and it allows you to proceed with your computation. You're not forced to know the type. It doesn't break Julia. It just gets slow under those circumstances, much like Python, MATLAB, and R. But the large majority of time, at least in scientific applications, it's possible to, or we really strive to make as much of the code inferable as possible. And that's really one of the key places where Julia's exceptional performance comes from. The next point I want to really emphasize is the elegance of writing Julia code. As a way of sort of illustrating that, I've done a lot of sort of work with and actually on Julia's array system, and I'm going to therefore choose an example from that. And one of the ways that I want to illustrate this is through comparisons with an amazing Python package actually called Dask. I'm not an expert Python programmer by any stretch of the imagination, but it's certainly one of the most impressive packages that I've yet encountered in Python. And Dask's goal solves something that my own lab really needed to solve, and that is, how do you handle big data? And so the way that Dask does this, and the way that we've gone in Julia also, very independently, really is to do something called lazy computation. So what is lazy computation? Lazy computation means that it's computation that only gets performed when you actually need the values themselves. You essentially declare what computation you want to happen when you need the values, but you don't eagerly, as the converse is often called, perform the computation itself. So this shows an example of creating a random array in Dask, and then adding it to its transpose and subtracting the mean along the first axis. And this all looks like it's an eager computation, and if X were of a different type, it would be an eager computation. But actually, this, no matter how big your data set, this line here runs almost instantaneously. And it would be this line here that actually triggers the computation that would take a long time, because this is when they're actually doing the computational work. This is essentially just a statement of the intent rather than the actual performance of a task. Now you might ask, might say, well, this doesn't really look like it helps much. And on its own, you'd be 100% correct. There is no major benefit really, I think, to doing this. Where the benefit comes from is when you can defer the computation for long enough that it really ends up being practically relevant. So I'll show you some examples in a minute in which I'm passing lazy arrays to an image viewer. And the nice thing about doing that is if you have some giant image file, like a terabyte sized image file on your laptop, and you're playing around with some different analysis ideas, it's really wonderful to be able to do all of those analyses in a lazy fashion and then pass the end results of that pipeline to an image viewer and see how your choices worked out, right? And the point is, you may only look at 0.01% of the data, but you don't necessarily know in advance which 0.01% of data. There may be like one little region of the image that happened where some event happens 230 seconds into the recording that you want to see what the whether your changes you made to your pipeline clarify the quality of the image in that particular spot or something like that, right? This depends upon the interactive feedback with the user. It's not predictable at the level of code that has been written far in advance of the particular data set that you're working with. And yet it would be very painful to have to do all of the do everything, snipping out each individual area ahead of time. So what's really nice is to declare your full lazy computation on the entire data set, pass it to an image viewer, and let the interactive exploration of the consequences of those computations be explored. And then once you make your decision, once you've finalized your pipeline, you've said, yes, this works great, I'm ready to commit to it, then you go ahead and actualize the entire computation, probably save the end result to disk because it may be too big to fit in memory. But you've saved an enormous amount of time, an enormous amount of programmer effort by doing things lazily rather than eagerly. Okay, so if you're working with big data, lazy computation is a really, really big deal. And that's what the sort of reason for existence for Dask, and it handles this in a very impressive fashion. Probably the most, at least in my own opinion, most sophisticated part of it is it has a system for handling what are called task graphs, and these are basically forced on it to sort of concatenate different stages of lazy processing together into sort of an overall understanding of what you're asking Dask to do, basically, so that it can sort of organize the computational pipeline for you in a manner that makes it feasible to execute on, say, hardware that's more limited than the size of the arrays that you're processing. Okay, and so that's pretty amazing. It's not easy to pull off. It's Dask.array, which is just one part of Dask, but it's the part focusing on arrays. It's about 12,000 real lines of Python code, and Dask as a whole, and it covers more than just arrays, is the effort of close to 500 contributors. They get a lot of funding for their work. So this is not anything to sneeze at. This is a very, very impressive effort by a lot of really smart people. But what I'm going to show you today is that there's at least a certain sense in which we can actually outdo them and do better than they can with just 20 lines of Julia code, essentially starting from scratch, right? The only thing we're relying on is Julia itself here, right? And that may be hard to believe, and there are ways in which that's not the whole or even accurate story. But in practice, for most tasks, it actually turns out that way. And I'll show you what I mean there. So first of all, let's show what those 20 lines of code look like. And I don't expect you to understand yet, because you haven't really started studying Julia, really any of the syntax here. I'm just going to sort of walk you through the kind of big picture things here, and you'll understand it at a much deeper level once you've had a chance to learn more of the language. So the way we're going to solve this is we're going to create a lazy array structure. So Dask has its own array structures. That's a key to its way of solving this problem too. And it turns out this is a good way to declare that. It's going to have two pieces, basically a function that we call in order to get values from the array. And then we're going to basically describe the axes, which in Python would be like the shape, MATLAB, we would call that the size of the array. Julia is actually even more flexible because you can use arbitrary indexing if you want. Okay, and then we have to define a couple of constructors, or it's actually helpful. It makes our users' lives more convenient. We could just always use the raw type to build this thing, but let's build some nice, easy to use constructors for our users. So this one here is useful if the user wants to control the element type of the output array manually, right? You may have something that you actually want it to convert the type for you before spitting back values, and so this allows the user to specify that. But if the user doesn't specify the output type, maybe we want to compute that either from the first value or by type inference if that's necessary. And that would be necessary if, for example, it's an empty array. Still, for consistency, we want to be able to declare an empty array that has a specific element type. And then we need a couple of utility methods, right? So those are the type and the constructor. So it's just essentially both build the raw structure. It doesn't really do anything yet at that point. But abstract array has a lot of predefined methods. So it turns out you only need to define a couple of things for you. One is the rule for getting a single value out of the array at a particular integer n tuple integer position within the array, basically. And so in this case, this is going to call the method that we created to fetch values. That's the only role it's going to be. So we're basically just hooking the method that the user will supply in as the way that overall this entire type of array operates. And then we also just simply need to expose that stored bit of information about the shape of the array to the outside world. So these are just, arrays can be very, very different from one another. There's no saying that they all have a function stored inside them or all have axes, stored as a field in the array. And so you have to provide these methods, but in our case, they're both fairly trivial. They just simply dispatch to whatever it's wrapping, okay? So let's actually try this out. So we're going to create a standard array. This is just a vector of 2 strings. And then we're going to define our function for fetching values from, in this case, the parent array. So it only takes as an argument the index I. So that's a counter going from 1. Julia starts indexing at 1. In this case, only 1 or 2 are only 2 options. And it's going to fetch the values then from the original, what I'll sort of think of as the parent array, but it's going to reverse the sequence of letters in them, right? And so that's the function. We've defined this function. It depends on this global variable A. This is not always good for performance. You'll learn that too about Julia, but we're going to ignore that for right now. And then let's create a lazy array out of this. So we're going to pass in the function, and then we pass in the shape, which is just the same as the shape of the parent array. And if we run this code, and then Julia, or sort of the Jupyter Notebook will print, Julia and the notebook will print the final value here, and you can see we've got a 2-element array. It's now an R lazy array, so the specific type of array we created. This means it has strings again as its element type. It's a 1-dimensional array, and so on. And you can see, indeed, it has reversed all of those arrays. Now, there is no such lazy array that actually exists. If I add one additional line here and I try to set the value of this, and I say, high class, and I try to actually set the first entry here, it's going to give me an error. And the reason is because we've not defined ways to set values in lazy arrays. And in general, lazy arrays, there are a few exceptions, but most lazy arrays really isn't a good way of setting values because the values that come out of it are arrived by a process of computation. And so there isn't any real place in memory to store this value that I tried to assign to it. Again, there are exceptions. There are some lazy arrays where there's essentially an inverse mapping in which you can set the values in the parent. And Julia makes that super easy when that's applicable. But in this particular case, that's not relevant to our interests here today. Okay, so, and in fact, I'd already set this up. I had forgotten that. Okay, so, all right, so this is super simple. We've clearly defined a lazy array. And I've made this dramatic claim that 20 lines of code needed to define that type in some way outdoes Dask. So there's a way in which that wasn't true, right? So Dask includes some amazing functionality for scheduling computations across a whole cluster of computers and all this kind of stuff. And for that, this code does none of that, right? And so, one of the Julia solutions that's comparable to that is this package called Dagger, and it's not a small package. So, the parts of Dask that are required for that kind of work are still relevant if that's what you really have to do. But the parts of Dask that are involved in things like the computational graph are not always needed. And the reason why is because part of the reason that people turn to complicated architectures, multiprocessing, parallel processing, distributed computing in Python is as a way of making up for its slow performance. And when you're using Julia, oftentimes you can do work on your laptop that other people using slower languages would turn to a cluster to do. And so in that circumstance, Julia's compiler becomes in fact a far better task graph manager than anything that can be provided otherwise. And it can generate optimizations that go all the way down to the hardware level that allow you to fuse multiple stages of computation in an efficient manner. So the place where something as simple as this 20-line bit of code is a major step forward compared to any of the other ways of doing something similar is when Julia's raw performance is fast enough that you don't need to bother with a lot of those more complicated things. I should also say, by the way, that Julia has native multi-threading. So if you have a multi-core CPU, you can you can use that with these 20 lines of code almost trivially, right? It's that thing where you may need to distribute computations across different machines where it gets complicated in both Julia and in other languages. So those 20 lines of code basically solve the problem for you, right? So and they give you essentially all of the widely used other features, right? So if you're working with arrays bigger than memory, all you have to do is load those arrays by mmap or any other lazy loading package. And a key thing is that it doesn't have to be built into that rlazy array type. It's composable with any other way of getting big data into your machine that you want, as long as it's an array, or as long as you can essentially just create a function for accessing values. I mentioned that you can use multi-threading, and Julia has native built-in multi-threading, and this is generally a lot faster than other forms of parallelism when it's applicable. And you can even use these kinds of tricks on GPUs as well. So why is this, though? I even made the claim that we're outdoing Dask. So the way in which it's really outdoing Dask is that because of the ways in which Dask is, or sorry, that Julia allows you to essentially do low-level computation, it gives you far greater flexibility. And as one example of that, one of the things that I would say Dask makes very easy is element transformation. If you want to say square a value before passing it on to the next stage of computation, that's super, super easy. But one of the things that's not so straightforward in Dask is if you want to say rotate an image or something like that in one stage of your lazy computation before passing it on to the next stage. And that is that Dask can operate very well on the elements, but not so well on the indices used to access those elements. The only way you can really implement those kinds of computation is to operate in chunks in Dask. And you pull in big chunks, you then pass your rotation operation to some underlying C code somewhere, and then wrap that back up in a lazy wrapper and pass it on. This ends up introducing some horrifyingly difficult to deal with problems, because what that establishes is essentially a minimum size of efficient computation for any later stage of your processing. And so anytime you want any bit of data, you have to take a whole chunk. So if your chunk is 100,000 or 10,000 pixels, let's say, and you're doing you're working on a computation that, say, blurs it by 1 pixel, again, like I mentioned earlier, in every direction. When you're operating on a chunk, you might need the pixels that are around the edge of the chunk. And so you may have to unpack 9 chunks just to process 1 chunk, for example. It's enormously wasteful in terms of computational efficiency. And in Julia, that's not necessary, because our implementation of these lazy operations was done on a scalar basis, meaning on a pixel by pixel basis. And so if you need just 1 pixel, you just go get that 1 pixel, okay? The other sort of, I think, Elements of ugliness are that, sometimes Dask has to make up for restrictions in other packages. So for example, in the excellent scikit images package, in order to deliver good performance to its users, it takes arrays of many different types of input, but it standardizes them to NumPy arrays before doing everything. And so if you accidentally pass a terabyte sized Dask array directly to a scikit image routine, boom, there goes your entire laptop or your entire computer, because it's now just tried to allocate a 1 terabyte array in actual RAM of the machine, and your machine may not be up to that kind of task, right? So it turns out that for all of the amazing work that's gone into development, there are just these fundamental, difficult to solve problems that beset you and that you end up having to deal with as the actual person just simply trying to get your analysis done. And Julia takes all that away because we can write optimizations that are targeted at a very, very low level. And this allows us to piece things together without really having to work very hard, without really having to think about it very much. So I do want to sort of show you one actual real live illustration of this, just so that you know I'm not lying to you. So I'm going to do a lazy loading of a video into the memory of my machine. And this is just something, this isn't a biological image. I've just because people come from different backgrounds, I took one of a nature scene. You'll see it in just a second here. I'm loading it, I'm faking it to make it look like it might be microscopy data. And so I've sort of decorated the description of the file format so that it knows that the axes have like a quarter micron spacing in the first 2 dimensions of the array, and that the third dimension of the array is actually time axis, and the frames were taken every quarter of a second, basically. And this is actually an RGB image, meaning that the actual elements of the array are colors, red, green, blue colors, rather than single scalar values. And so we can play this, we can pass this array into a video player, and I may have to go off of full screen here. So yes, there it is. And so here you can see the movie that I'm starting with, basically. So obviously it's not a microscopy image. I'm just kind of faking it that way just to make it a little bit more interesting. Python has packages like xarray, which allow you to do these kinds of things as well. Okay, so that's the raw input. This actually is, I'm not going to pause to show it to you, but this is a lazy loaded array. It's loaded by mem mapping, and I haven't set the right permissions in the file, so I can't actually write pixels to this array. Okay, so now what I'm going to do is some manipulations. So if you're doing an experiment, often there are sort of key moments in time, and these may not be equally spaced apart from one another. It may not be every third frame. It may be a cluster of frames here, followed by a gap, followed by a cluster of frames here, followed by a gap. And what we're going to do is we're going to sort of pull out a subset of them. I'm going to mimic this by just pulling out a random subset of frames. So here's a set of random numbers. And then what I'm going to do is I'm going to create a view, which is like it's a subset of the original movie, a temporal in this case. I'm only showing a subset of the time frames. And if I show you this movie, you can see that it now kind of stutters a little bit, and it also plays a lot faster. It's about half the number of frames. And the stuttering is because of these sort of random gaps in the movie, right? And so it's important to point out that this again is a lazy movie that I haven't had to allocate any memory to store that. And it's for those who may be accustomed to views in other languages, one of the key points to keep in mind is this is not a so-called strided array. These are, since they're not regularly spaced, there's no sort of like, let's say, pointer offset that's regular across it, but I nevertheless get outstanding performance, as you saw in the movie player, even though it is an assumption it can't make. Let's do a further manipulation. I'm just going to drop the red color channel. I'm going to use a package here called mapped arrays, but that's actually almost the same thing as our lazy array that we created earlier. And so if we look at this and we play this movie, oops, where did it go? There it is. Now you can see everything looks kind of cyan colored because we've dropped the red color channel. So this is another lazy manipulation on top of the frame selection, right, that we've made. Let's do another layer here, and this one's going to be the really fun one. We're going to use our lazy array that we created. We're going to define a rotation, and the angle of the rotation is going to depend upon the time coordinate. We're going to capture, to solve that sort of issue about global variables that I mentioned earlier, we're going to capture the image inside of a function that we return as the lookup function. And then we're going to have that be applicable over the axes of our array. And if we do this, and we again let it open up another visualization window, now here you can see our movie is spinning around, right? And so we're doing these spatial transformations on the indices, we're dropping color channels, we're choosing subsets of times. All these are many different layers of lazy processing that are going on, and they were trivial. They were super, super easy. We hardly had to do any work in order to put these things together. We're getting outstanding performance on the other side. It's perfectly happy to play even a 1 megapixel, spatially movie at 30 frames per second on my laptop, at least when I'm not on Zoom. And the performance is really, really quite exceptional. So the thing I think that the point that I want to make about all of this is that we were able to use just one dumb video player, didn't care about the types of the videos or the specifics of the arrays that I was passing in, anything about their internal details. All that was stuff, though, that the compiler cared about, and the compiler specialized the operations so that that entire computational pipeline gets squished down into the most sort of direct way that Julia's compiler can figure out how to implement that computation. And all of these packages can be combined together without any kind of conflicts. You don't have to do the kind of thing that Scikit Images does to convert every array that comes in into a NumPy array, for example. It all just works together very seamlessly, and it all works together very efficiently, and it lets you get done stuff that you just don't have to think about in far fewer lines of code with better performance. Okay, so, oh yeah, and just to sort of show you the scale of the performance here, if we benchmark just the extraction of a single pixel here from the end result pipeline of our whole lazy array, you can see here, I'm on Zoom, so it's a little bit slower than it often is, but it's about 33 nanoseconds or so per pixel. And again, that's fine for playing an entire megapixel sized image on my laptop at 30 frames per second. So these low-level optimizations that Julia makes efficient also, in addition to just making things that you might be able to do in other languages, although they might be too slow to be practical, it makes them easy to the point of being almost trivial in Julia. It also lets you do things that are really almost impossible by other means. And as a final example of that, I want to mention briefly a cool set of packages for solving optimization. So if you're trying to solve an optimization problem and the function you're trying to minimize isn't shaped like a bowl, but instead has multiple minima to it, you might ask, how do you know I found the best minimum? And kind of for years, I thought that the answer to that question was, well, there isn't a way to know that. You can't check all values, and therefore there's no way you can be sure there isn't a better value lurking somewhere. You just do the best you can, right? And so at least for me personally, that was sort of the accepted answer. It turns out actually that there is an exact answer to that problem. And it comes down to being able to sort of actually exhaustively check all the function values using a more efficient approach than checking each of a infinite number of locations. And it's to use a branch of mathematics called interval arithmetic. So in interval arithmetic, if we use the interval arithmetic package, we can create an interval. This denotes essentially all continuous numbers between 2 and 3. And in Julia, because we can optimize at a very low level, we can define mathematics of intervals. And so if you square values that are no smaller than 2 and no bigger than 3, then you can promise that the result of squaring them is no smaller than 4 and no bigger than 9, right? And if you add 2 of those numbers together, you can promise that the result is no smaller than 4 and no bigger than 6. Interval arithmetic has some serious annoyances with it, and one of the easiest ways to illustrate this is what happens if instead of adding these numbers, we just subtract them. You might think that, of course, the answer would be 0, and in interval arithmetic, unfortunately, it's not. And that's because unless you happen to know that these really always meant the same number being subtracted from itself, you might be subtracting 3 from 2 or 2 from 3, and hence the default answer in interval arithmetic is to return the widest possible range so that there's a guarantee that you'll never be beyond these, right? It's not clear whether these are the same interval or different intervals that or different variables that represent the range from 2 to 3. Okay, so with that in mind, that there's some sort of, let's say, conservativeness that sort of is not as tight of a bound as maybe it could be, interval arithmetic can let you solve a lot of problems. Because if you're trying to minimize f and you can evaluate f over not just at a single location, but over a whole span of locations, and you get an interval out, then you know that f is never going to achieve a value that's smaller than c. So this lets you put a lower bound on the smallest possible value that might be in an entire finite sized region. And this lets you, in fact, check an infinite number of locations in finite time, basically, right? And so when doing this, you can take functions that have complicated shapes. If we plot what these functions look like, here's an example of a test function for global optimization. And you can see this has many, many different minima. It has 4 equivalent minima. You'd like to, find one of those best ones. And if you use this so-called interval optimization package and ask for the minimum over this 10 by 10 array, it gives you several options. And this has to do with some of the challenges of using interval arithmetic, but in fact, all of these encompass the 4 equivalent global minima. So there's no way you're going to miss the global minimum from an analysis like this. Okay, so again, this is just an illustration that there's actually even whole new approaches that you can use to tackle what look like almost insoluble problems when you can design your entire computational pipeline to operate on the lowest level, the most primitive computations, in this case, just arithmetic itself, right? So as a summary, Julia is, still young. It still has rough edges and holes, but it's growing up awfully fast. And it's really enabling some of the most, I think, exciting developments in computing. And it really lets you write your code in a more general way than any language I've encountered before. It more reliably gives you world-class performance. And it lets you combine the efforts of many different people, almost like Legos, into a greater whole with very rare obstacles in doing so. And so it's really an incredibly efficient tool. It's easy to underestimate, I think, what you can do already with Julia, right? Some ecosystems have, 10 to 100-fold more packages than Julia, but sometimes in Julia you can accomplish what might look almost impossible simply by combining packages in creative ways that aren't possible otherwise. And with that, I will stop the recording. And thank you for your attention.